MI based on positioning of 2-point load and absolute maximum effects. Introduction. In structural engineering, the assessment of maximum effects of loads on beams and structures is crucial for safe and economical design. When structure is subjected to moving loads, such as vehicles on a bridge or machinery on a platform, the location of these loads significantly influence the internal forces and movements developed within the structure. A, pu- a two-point load system is a simplified model often used to represent concentrated loads, such as wheels of a vehicle or two heavy equipment points. Determining the Determining the absolute maximum bending moment, shear force, or deflection requires careful consider- consideration of how these loads move across the span. By analyzing the position of 2-point loads, engineers can determine the critical positions that produce the absolute maximum effects in the structure, which is essential for design and safety verification. This method ensures that the structures can withstand the worst case scenarios without unnecessary over design. Fundamentals of machine learning based load positioning. The study of moving loads is essential in structural engineering, particularly for bridges, crane girders, and other structures subjected to variable loads. The fundamentals revolve around understanding how the position of loads affects internal forces like shear, bending, movement, and deflection. The concept of moving loads is a load that changes its position along a structural member, such as vehicles on a bridge or trolleys on a crane runway. The maximum effects do not necessarily occur when the load is at midspan or supports. It depends on the interaction of the load positions and the structural response. The proper positioning analysis ensures safe design against worst case scenarios. It prevents overestimation and over of bending moments and shear forces. Modern design codes example ASSTO for bridges, IS 456 for concrete incorporate moving load factors based on such analysis. Machine learning techniques applicable to load positioning. Machine learning can help to predict, optimize, and analyze the effects of moving loads on structures, especially when analytical solutions become complex due to multiple loads. Variable load pattern or real-time monitoring requirements. The goal is to determine critical positions of load that produce maximum internal forces or stresses efficiently. First one, supervised learning. It it predicts the structural response, example bending moment or shear or deflection given by specific load positions. Reinforcement learning optimize the load positioning to achieve maximum or minimum structural effects. Unsupervised learning identify patterns or clusters in load effects data. Evolutionary algorithms evolutionary algorithm optimize the load positions for maximum internal forces. Hybrid techniques combine the strengths of machine learning approaches for better predictions and to optimization. Practical consideration. Machine learning models require large and accurate data sets from simulations, experiments, or sensors. Data requirements for training machine learning models. The machine learning models, the success of any machine learning model depends heavily on the quality, quantity, and relevance of the training data in the context of load positioning on beams, bridges, or other structures. The data must be accurately capture the relationship between load positions and structural responses, such as bending moments, shear forces, and deflection or stresses. First one in input features. These are the variables that model uses to learn the mapping to output labels. These are the responses from the model predicts. Third one, data generation. I use structural analysis software, example SAP 2000, ANSYS, StatPro, to simulate the effect of different load positions. Hybrid approach. Combine the simulation and field data to improve model generalization. Volume and data volume and diversity. A large dataset converging all possible positions is necessary for machine learning models, especially for neural networks. Pre-processing requirements. Normalize or scale input features to improve model convergence, remove unrealistic or physical impossible load positions. Quality considerations. Avoid bias towards particular positions, example midspan only. Include noise tolerance if field data is used. Predicting absolute maximum effects with machine learning models. Predicting the absolute maximum effect bending moments, shear forces or deflections due to moving load is in structural engineering for safe and economical design. Machine learning offers an efficient alternative to traditional analytical or iterative methods, especially for complex load configurations or real-time applications, like problem definition, that determine the critical positions of moving loads on a structure that cause the highest internal forces or deflections. Data preparation. In data preparation, there are some features like input features, output labels, and etc. Include edge cases. The Lonius supports maximum spacing to ensure the model captures absolute maximum. Third one, model selection. In model selection, we need to use the regression models, the neural networks, ensemble models, and reinforcement learning. Fourth one, trading and validation. We used to simulate use simulator or experimental data for training. Ensure the dataset covers all possible load positions. Split data into training, validation, and test sets to prevent overfitting. Advantages: speed, flexibility, automation, and monitoring systems. Seventh, sixth one, practical implementation. Generate a comprehensive dataset via structural simulations with varying load positions. Train a neural network or ensemble a model to predict internal forces. Update the model periodically with new field data or improve accuracy. Practical implications in structural design and safety. Practical implications: the prediction and analysis of absolute maximum effects of moving loads have direct impact on the design, safety, and serviceability of structures such as bridges, crane girders, highways, and industrial platforms. So machine learning techniques further enhance these aspects by providing faster, more accurate, and adaptive predictions. First one, design optimization. Accurate critical load identification. In machine learning models can quickly identify load positions that produce maximum bending moments, shear forces, or deflection. Second one, enhanced safety. Worst case scenarios analysis. The machine learning can predict extreme cases that may not be obvious from traditional methods, ensuring structures are safe under all loading conditions. And dynamic load effects. Real world loads like traffic, traffic, cranes, and moving machinery vary with time and speed. Machine learning models trained on such data can account for dynamic loading, which is crucial for safety verification and real-time monitoring and decision making, like bridge and highway applications that can process sensor data in real time to predict whether moving vehicles may cause critical stresses, enabling traffic control or load restrictions. Time and cost savings. Reduce simulation requirements. One trained machine learning ML models can predict maximum effects without running full finite elements full finite elements analysis for load scenarios. And machine learning based load positioning enhances both safety and efficiency, allowing engineers to design structures that are robust against worst case scenarios without necessary over design. Conclusion. The analysis of moving loads and their positioning is a fundamental aspect of structural engineering, crucial for ensuring the safety, reliability, and efficiency of structures such as bridges, crane, cane girders, and industrial platforms. Determining the absolute maximum effect bending moments is shear forces and deflections requires careful consideration of load positions, magnitudes, and structural characteristics. The practical implications of ML based load positioning are significant. It enables cost effective structural design, the effect, efficient material use, with proactive maintenance, and real time safety monitoring by integrating ML predictions with traditional engineering analysis. Structures can design to withstand dynamic and variable loading conditions with high confidence while also minimizing over design and construction costs. In conclusion, the combination of moving load analysis and machine learning represents a forward looking approach in structural engineering, providing accuracy, efficiency, and enhanced safety in both design and operational stages. Thank you.